Hello, my name is Ayron Gors, and this is my Project 9 presentation for CE570. I've highlighted the objectives of this week's project above, and overall it's extremely similar to last week's project, only now we are tasked with finding the body force density of our total body, and then verifying the total force in one of our bodies by using the equation that you can see right here. And defined below is my symmetric Cauchy stress tensor as we're tasked with defining for this project, which is the same exact tensor that I used last week. And moving on, you will see how this tensor was manipulated in order to obtain the body force density and the force. This slide is just highlighting my Cauchy stress tensor as applied to each of my two composite shapes, and my shape is still my silo. And I went over this slide in detail last week, so if you're interested on how I derived these different components of my code, please see last week's project. Now I'd like to highlight how I derived my body force density needed for the equilibrium on my body of my choosing. And as you can see, the definition of the body force density is just the negative of the divergence of my Cauchy stress tensor. And you can see the broken down form of that equation, as you can see here, is just the Cauchy stress tensor multiplied by the gradient. And as you can see, deriving through all my math here, in general, my body force density is equivalent to the negative 0, 0 for the E1 and E2 components of the vector, and a negative 3 and negative 9 x3 squared for the E3 component of my vector. And then you can see also my body force density as applied to my two composite shapes, my hollow hemisphere and my hollow silo. And you can see that all I needed to do was replace this x3 component with the third component of my parameterization of those shapes. Now I'd like to demonstrate my code running for you, and as you can see, this is my week 9 project. You can see my code as defined here is still my silo, and all my input parameters of R1 and R2 and everything like that. The first component of my code is my hollow cylinder, and you can see all the appropriate parameterizations and everything, and then my Cauchy stress tensor and my body force density as defined right here, as you can see. And then moving on, my second component is my hollow hemisphere, and you can see the parameterizations and everything else that make up my shape, and you can see the symmetric Cauchy stress tensor as well as my body force density for this specific shape, as you can see here, and then for plotting purposes, the Cauchy stress tensor. Moving through the rest of the code, you can see I haven't hard-coded anything in, so if we give this a run, you'll see the output as defined. It spits out this shape, as you can see, with all the tensor field and the stress field, as you can see here, and then you can also see in the command window the outputs. As you can see, the shape is in equilibrium as more or less everything is equal to 0. So moving on, I will define how this was achieved. We were tasked with verifying the force on one of our composite bodies of our choosing, so I'm going to go ahead and choose body 1, which is my hollow cylinder, as you can see here, for the force equation to verify against the MATLAB output. And finally, I'd like to highlight my verification calculations for my body force density and my force that I obtained for my hollow cylinder. Up above there, you can see the definition of my body force density just in general, and then applying that to my hollow cylinder as defined previously, you can see my body force density vector is defined right here. And then in order to obtain the force across my entire body of my hollow cylinder, I have to integrate that with respect to the volume of my cylinder. So my cylinder is made up of 3 components: a height, a radius, as well as an orientation of theta. And as you can see, I have to plug in my body force density vector into the equation for the force is defined right here. And as defined in previous projects, my volume Jacobian is just equal to R. And then integrating it across all my 3 parameters that make up the height, the radius, and that orientation of theta as defined right here is negative 12, 18 to 20 for the radius, and then 0 to 2 theta for, or 2 pi for theta. And just all we have to do is just integrate that with respect to these 3 components, the theta, the radius, and the height. And just working through my math, you can see that I obtained 0 in the E1 location, 0 in the E2 direction, and a negative 1,246,332.638 in the E3 direction, which is exactly matches my MATLAB output as shown here. And due to my forces being super large, you can see that my net force on my total composite body is relatively in equilibrium, but not quite. But that is just due to how large my forces are. So thank you for watching.